Okay, so we're continuing on talking about nuclear chemistry. I'll give you a few seconds to copy this down. All right, so far in section A of the chapter, we were talking about natural radioactivity that occurs in nature, and we talked about the different particles that are involved in radioactivity. We talked about measuring radiation, nuclear reaction or equations, radioactive decay series, half-life, stability. And now what we're going to do is we're going to talk about induced reactions. These are reactions that are started by man, that we cause to happen in nuclear reactors, okay, underground. So in section 2012, transmutation through nuclear bombardment, this happens in a particle accelerator, and actually the alchemists were right. We can, in fact, change lead into gold, but not by normal chemical means that they were trying to use. We can do that in a particle accelerator, and that is through nuclear bombardment reactions. And this is a non-spontaneous nuclear reaction that is forced to occur when the nucleus is struck by a high energy particle or another nucleus. So when we smash atoms. Okay, this is also how some of our newer elements that are man-made, that don't last very long, have been discovered, that are towards the end of our periodic table, is by crashing atoms together. So there are two types of nuclear reactions we're going to talk about when we use nuclear bombardment. And the first is fission. So go ahead and pause your video and copy that down. Okay, now nuclear fission is the splitting of an atomic nucleus into two smaller, more stable nuclei. And I have an equation written down that's an example of this. Now the N10 is a neutron, having a mass of 1 and a charge of 0. So we can bombard uranium-235 with a neutron, and actually there's more than one reaction that can occur, and there's probably even more than these two that I've written, but two reactions that can happen is it can break down into barium-139 and chromium-94, releasing 3 more neutrons and a lot of heat. It can also break down into cesium-144 and rubidium-90, releasing 2 neutrons and a lot of heat. And looking at this, where the heat comes from is some mass is converted into energy. Now, you cannot tell from the equation balances mass-wise, but when they actually use the empirical data directly from experiments, they find that they have less mass than they started with. And we can actually take a look at Einstein's equation of relativity, E equals mc squared, and this is where that applies, because c is the speed of light. And so if you square the speed of light, which is already a really big number, and you have a very small mass, you can still get a lot of energy from it. And so that is what we see with nuclear fission. Now, with nuclear fission, we can get what's called a chain reaction. This is a self-sustaining fission process in which neutrons produced from fission reactions cause more fission reactions. So up here, you see how we bombarded this uranium atom with a neutron and how it produced 3 more neutrons? Well, those 3 neutrons can bombard 3 more atoms, and when they bombard 3 more atoms, 9 more neutrons are released. And those 9 neutrons bombard 9 more atoms, and then 27 are released, and so on and so forth. So you get this chain reaction that's really exponential. And you do, though, have to have a certain amount of mass to have it, and that's called the critical mass. This is the smallest mass of a fissionable substance that can sustain a chain reaction. If you have a mass smaller than the critical mass, which is called subcritical mass, you will not get a chain reaction. You have to have a certain amount of mass, and we'll talk about the application here in a minute. Go ahead and copy the rest of these notes down for fission. Okay, we can also have what is called supercritical mass, and this is the amount of fissionable material that can support an explosion, an uncontrolled chain reaction. And so where the critical mass and the supercritical mass really apply is in nuclear reactors versus atomic bombs. In a nuclear reactor, we do not want what's called a meltdown. We do not want an explosion in that. We want something that is sustainable and controllable. So in a nuclear reactor, the reaction is controlled, so just enough reactant is present to maintain the chain reaction. So we're just right at that critical mass, and we're able to actually control that. And they have numerous ways that they control that I'm not going to get into. But I know if you have questions about that, Sam Olson knows a lot about this, so you can ask him. Now, atomic bombs, the reason they are explosive is because they have supercritical mass of fissionable material, which reacts violently and explosively. Definitely two very different uses here for the material. And so again, we can get into that discussion of good ways we use information we've gained from science and maybe not so good ways that we use the information from science when we talk about nuclear reactors versus atomic bombs, because we've already said that in nuclear reactors, and the one thing you need to know is that with a nuclear reactor, the usable product of the nuclear reactor is thermal energy. We are after the thermal energy because what we do with that energy is we produce steam from water that turns turbines. And those turbines turn magnets that are inside of wire coils that will get electrons flowing in the coils and produce electricity. We talked about that in physics last year, or if you haven't had physics yet, we'll talk about it next year. And so that's what we're after, is the thermal energy to turn the turbines. And we don't want an explosion from that, like Chernobyl, where they had a meltdown. It wasn't an explosion, but it did get out of control. And actually, I believe the book says, and you can check the book on this, about 20% of our electricity in the United States is produced from nuclear reactors. Some countries get most of their electricity from nuclear reactors. One of those being France, I believe, which it said produced 80% of its energy from nuclear reactors. So nuclear reactors, when they are managed properly, are a relatively clean form of energy. Yes, there is nuclear waste from them that we then have to figure out what to do with, which is a real challenge because nobody wants that in their backyard. Okay, now, so fission is one of these nuclear reactions from bombardment. The other one is fusion. Nuclear fusion. This is the transmutation process of combining two or more smaller nuclei into one larger, more stable nucleus, releasing great amounts of energy, the opposite of nuclear fission. And we can see here, if we combine two hydrogens, now notice they're different isotopes, we can produce helium and a neutron. And this neutron will keep the chain reaction going. Now, the problem with this actually is an important reaction for us. Without it, we would not be able to survive, okay? God created this reaction, and it is going on right now in the sun. And without the sun's energy, there would not be sustainable life on Earth. So this is a very important reaction to us. The problem with it, we would really like to harness this energy for our use here on Earth, because 1 gallon of water, because we would obtain the hydrogen from water, 1 gallon of water would be able to produce the same amount of energy as 300 gallons of gasoline, if we were able to use this form of energy. And it would be very clean. It does not, unlike fission, it does not produce nuclear waste. It just produces helium. We can, obviously, we have hydrogen bombs. We can cause this reaction, but it's hard to control and it's hard to sustain because it does need really high temperatures. And the sun happens to have high enough temperatures to keep this going. And one of the problems to keep it going is having materials to contain the reaction. They do have some ideas. You can read about those in your book. I'm really not going to get into them, about being able to contain that reaction. One of them, I believe, using magnets. But the sun, this has to occur under very high temperatures, very high speeds, and the sun, because of its high temperatures, is able to maintain those high speeds of how fast those atoms need to come together, because the sun is so hot. But again, the sun would melt anything and vaporize anything of the normal materials that we have that would contain this. So scientists are still working on this, and they would really love to harness the energy from it. So I'm going to wrap this up here. There are no extra problems or anything, and I will be back with synthetic elements and mass defect next time.